Hello everyone. In today's lecture, we will cover one exercise on counters, which is taken from GATE 2021 exam. So here you can see for a given figure, correct? So the propagation delay for XOR gate is given as 3 nanoseconds here. So which means that whenever the outcomes produced by this XOR gate from the inputs, it takes 3 nanoseconds to process that. Okay, so here we can mark that here, and we can say the propagation delay T PD for XOR gate is 3 nanoseconds. Correct, 3 nanoseconds. Now the next input which is given is the clock. So here the clock frequency is 500 megahertz. Correct. So this is my clock frequency CLK. Clock frequency F is nothing but 500 megahertz. Correct. That's the common clock, positive triggered edge clock for all the flip flops. And it says that the starting value or the initial value of all the flip flops is Q2, Q1, Q0 equals to 111. Q2, Q1, Q0, they are 111. Okay. So my initial state, initial value, or you can say initial state, Q2, Q1, Q0, they are 111. Okay. So far, so good. And it says D2 is also initially set it to 1. Okay, so my D2 is also 1 here. So these are my initial states, right? So now it is asking us to compute the minimal number of triggering clock edges after which the flip-flop outputs become 1, 0, 0. Correct? So which means it is asking us to compute that after how many edges, correct? After how many edges of the clock, my Q2, Q1, and Q0 become 1, 0, 0, right? That's what we have to compute. So far, so good, correct? That's what we have to compute. So let's see what we have here. Let me draw the different color pen. So here, let me draw the clock first so that we can explain nicely. So here you can see my clock frequency is F is equals to 500 megahertz. Correct? As we know that my time cycle time of one particular cycle T is equals to 1 by F, which means 1 by 500 megahertz. So can I write in this way? 1 by 500 into 10 power 6, which comes to 2 nanoseconds. Correct? So my time of each cycle is 2 nanoseconds. Now, what does that mean? Okay, what does that mean? So let me draw my clock now. So this, let's say this is my clock. Okay. So this clock is same for all the flip-flops. And since there is no ball given here, that means it is a positive edge clock, positive edge triggering clock, right? So we got all those. So now you can see we have to compute the edges after which this happens. So this I'm going to mark as slightly with a different color. So this is called my edge number first, right? So this is called my edge number 1. So before that it is initial state, right? So which is called 0. So after that first edge, this is my second, third, 4, 5, 6, 7, and so on. Okay, so on, right? So my first edge happens at 0 nanosecond. So here you can say this is my 0 nanosecond, correct? And this cycle is of 2 nanoseconds. Now each cycle is of 2 nanoseconds. Each cycle is of 2 nanoseconds, correct? Right? As we said, each cycle is of 2 nanoseconds. So I'm just marking my 2 nanoseconds for each cycle. 2 nanoseconds for each cycle, correct? Now let's draw the table and make a count so that we can identify after how many clock pulses I get my outputs at a state of 1, 0, 0, right? So let's take a clock first. So that's my clock. Then I have to find out my D2 because based on it depends on which inputs it gives. Now, which is nothing but D2 is nothing but this is my Q0 comes here. So that's my Q0, which is getting XORed with Q2. Correct? So D2 is nothing but Q0 XOR Q2. Now, please note that the propagation time for the XOR gate is 3 nanoseconds. Okay, so keep that in mind. We will use it frequently. These are my Q2, Q1, and Q0s, right? Q2, Q1, and Q0s. Okay, so that's my table that we have to compute. Clock. Okay, so now let's take the initial condition, first condition. Let's take the first condition, which is at 0 nanosecond, right? That's the first one, 0 nanoseconds. I mean, okay, initial condition at 0. So age numbers. So before the age 1 happens, that is my 0, right? So first initial state, as we know that D2, the initial state is given D2 equals to 1. Initial state is given D2 equals to 1, and my Q2, Q1, and Q0, they are 1, 1, and 1. Okay, so far so good. Correct. Now I want to compute what happens at my first edge when this happens, right? So I'm saying my first edge, when this comes here, what happens? My first edge, when this comes here, what happens? So this we said at 0 nanoseconds. Correct. Please note, I'm not computing any time at 0 because 0 is because this is an initial condition. So when the first edge happens, I considered at a 0 nanoseconds. Correct. Now please note, XOR as 3 nanoseconds. Correct. So it will not pass any new values. It will hold its initial condition D2 equals to 1, which was already there. And this would be passed to Q2 as per the excitation table of D flip-flop, correct? And Q2 will be shifted to Q1 and Q1 will be shifted to Q0, correct? So far so good. Q2 will be shifted to Q1 and Q1 will be shifted to Q0, correct? So now you can see I got my state at 0 nanoseconds. So this is my state at 0 nanoseconds. Now let's say the next edge comes. Now let's say the next edge comes, which is number 2, correct? Which comes after 2 nanoseconds of the first one, right? So second edge comes after 2 nanoseconds. So this is my 2 nanoseconds. Okay, this is my 2 nanoseconds. Now please note, here you can see my D2 equals to Q0 XOR Q2. So actually my XOR becomes 0 because it's an inequality detector. So when both the inputs to XOR, if they are same, the output of the XOR becomes 0. However, propagation delay for the XOR gate is 3 nanoseconds. So it will not pass the latest output to D2. It will hold to its older one because this is coming at 2 nanoseconds and would be given to Q2. This becomes 1. This is going as shifting to Q1 and this is getting shifted to Q0, correct? And this is at 2 nanoseconds at the edge number 2. At the edge number 2. This is at 2 nanoseconds, right? Now let's see what happens at third edge. So now 2 plus 2, this comes after 4 nanoseconds. Third edge comes after 4 nanoseconds, correct? Now please note, XOR has the delay of 3 nanoseconds. Third edge comes at 4 nanoseconds. So this XOR transition would be passed to D2 at this point of time, somewhere in between, correct? So now my Q2 XOR Q0 is nothing but 0 because it's an inequality detector and which would be passed to D2 at 3 nanoseconds, right? So at 4 nanoseconds, when this edge comes, when this edge comes, we have the latest input passed to Q2, which becomes 0. This one getting shifted to this position of Q1 and this one is getting shifted here. So this is my state at 4 nanoseconds, correct? This is my state at 4 nanoseconds. Now let's see the next clock comes at age 4. H4, which is coming at 6 nanoseconds, correct? Just the addition of 2 plus 2 plus 2, 6 nanoseconds. So age number 4 comes at 6 nanoseconds, correct? So the next state is now we want to see at age 4, correct? At age 4, which comes after 6 nanoseconds, right? Which comes after 6 nanoseconds. So you can see the value of Q2 XOR Q0, right? So at this point of time, won't be reflected because XOR delay is 3 nanoseconds. So it's going to keep and hold on this older state rather than passing the new state because of the propagation delay. So now this 0 gets transferred here. This 0 gets shifted here at that particular clock pulse, and this one comes here, correct? This one comes here. This is at 6 nanoseconds. This is at 6 nanoseconds. Now, what happens at the next edge? Let's take a look. So now at fifth edge, which comes after 8 nanoseconds, which comes after 8 nanoseconds. Now you can see my XOR, correct, will pass the new value because the propagation delay was of 3 nanoseconds, right? So it will pass definitely my new value, correct? So this is nothing but XOR of Q2 and Q0. So XOR of Q2 and Q0 would become 1, and that would be given at the input of D2. That would be given at the input of my D2. And this 1 comes here, this 0 comes here, this 0 comes here. This happens at 8 nanoseconds, correct? So if you observe, this is my expected state of output. This is my expected state of the output, correct? This is my expected state of the output, which happens at fifth edge, which becomes 1, 0, 0. So you can see we were asked to reach the state Q2, Q1, Q0 equals to 1, 0, 0. And we are reaching it, that particular state, after 5 edges. If this question can be asked that after how many nanoseconds we will reach that particular state, so the answer is after 8 nanoseconds, we will reach this particular state. So please note here, the key role is played by the XOR's 3 nanoseconds delay. If you have any questions, please drop the comments or you can reach me out. We will address your questions. Thank you very much.